In the last couple of classes, we've talked about polynomial time reductions to translate between problems and certificates and verifiers to show that problems are in the class NP. This time, we're going to put those two concepts together to define NP-completeness and establish what we mean when we say that a problem is provably hard. When we talked about polynomial time reductions, we said that when we prove B is polynomial time reducible to A, the intuitive meaning is that problem A is at least as hard as problem B. Building on this idea, a problem is NP hard if it is at least as hard as any problem in the entire class NP. So formally, an NP hard problem is one where, for any problem in NP, that problem can be polynomial time reduced to A. In addition, if a problem that is NP hard is itself in the class NP, then we call it NP complete. So when we think about a comparison between the classes P and NP, we proved before that the problems solvable in polynomial time are a subset of the problems verifiable in polynomial time. And the famous P not equal to NP conjecture says that this subset relationship is strict. If the conjecture is true, then there are some problems that are efficiently verifiable, but not efficiently solvable. And if such problems exist, then the NP-complete problems are among them. So if we have NP-hard problems, ones where every problem in NP can reduce to them, some of those problems might be in NP, and some of them might not be in NP, which means that the overlap of the NP hard problems and NP is the set of NP complete problems. Assuming that P and NP are not equal, there is no overlap between P and the NP-complete problems, because if we could solve an NP-complete problem in polynomial time, then we could solve anything in all of NP in polynomial time, so that could only be true if P and NP were equal. The idea that NP-hard problems should exist is kind of wild, because the class NP includes all of the decision problems we've talked about all semester, and many, many more as well. And if we're saying that problem A is NP hard, we're saying we can take any of those problems and efficiently translate them into problem A. But the amazing thing is that there are NP-complete problems. Specifically, the Cook-Levin theorem establishes a first NP-complete problem. It's worth noting that Cook and Levin originally proved that Boolean satisfiability was NP-complete, but we will stick with the version in our textbook that uses circuit sat, and these two versions really are equivalent. But it's worth pausing for a moment to marvel at the idea that we have an NP-complete problem. What we're saying here is that circuit sat is a member of the class NP. That's a thing that you have essentially proven through the combination of your homework, where you designed a polynomial time algorithm for circuit eval, and the in-class exercise where we showed that such an algorithm gave us a verifier for circuit sat. But this problem, which is in the class NP, can represent any other problem in the entire class. Every decision problem that is verifiable in polynomial time can be efficiently converted into an instance of circuit sat. The book tries to provide some intuition for this by giving examples of how to represent certain problems as circuit sat, and they also talk about how fundamentally computers are built from circuits, so maybe it makes sense that things we can efficiently compute can be represented as polynomial-sized circuits. But what the book provides is far from a proof of the Cook-Levin theorem. The full version of this proof uses Boolean satisfiability and shows how the entire execution of a Turing machine can be encoded as a Boolean formula, and that Boolean formula is satisfiable if and only if the Turing machine would output yes. That proof is way more than we have time to get into here, but if you're interested, I encourage you to take theory of computation. But as a consequence of the Cook-Levin theorem, which establishes a first NP-complete problem, there are lots of interesting things we can deduce. First of all, once we have an NP-complete problem, we can use it to identify other NP-hard or NP-complete problems. Specifically, because we know that polynomial time reducibility is transitive, if every problem in NP reduces to circuit set, and circuit set reduces to problem A, that means every problem in NP reduces to problem A, which would mean that A is NP-hard, and if A is also in NP, then it's NP-complete. Once we have established some NP-hard problems, including circuit set or others that we get by reductions from circuit set, if any of those NP-hard problems have a polynomial time algorithm, then we could solve every problem in the entire class NP in polynomial time. Because our polynomial time reductions would let us take an arbitrary problem and convert it into that NP-hard problem in polynomial time, and then our polytime algorithm could solve that instance efficiently and give us an answer to the original problem. So if you find a way to efficiently solve any NP-complete problem, you would have proven that P and NP are equal. On the other hand, the contrapositive of this statement is that if P and NP are not equal, then for any NP-hard problem, there cannot be a polynomial time algorithm. And this is fundamentally the reason why we have been studying reductions, verifiers, and NP-completeness. Because computer scientists generally believe the conjecture that P is not equal to NP, and there's good reason to believe it because we have found no evidence to the contrary despite decades of searching. If we can prove that a problem is NP-complete, that means that the problem cannot have a polynomial time algorithm. So, all semester we have been proving that various problems are solvable in polynomial time by providing efficient algorithms. But for the problems we have been unable to efficiently solve, we now have a tool for proving that they cannot be solved in polynomial time. And that is to prove that the problem is NP-complete. So our goal now is to show that various problems are NP-complete, and we do that using the techniques from our last two classes, giving a certificate and verifier to show that the problem is in NP, and then giving a polynomial time reduction from some NP-complete problem to show that the problem is NP-hard. Right now, we have only one NP-complete problem, and so our first reduction has to be from circuit set to some other problem. But once we have established additional NP-complete problems, then we can use any of them as the source problem for our reduction in showing that a new problem is NP-hard. And for the remainder of this video, I want to apply our template to prove that the 3-sat problem is NP-complete. In 3SAT, we are given a Boolean formula in 3CNF form, which means that this formula is a bunch of clauses all ANDed together, and each clause is an OR of 3 literals. The answer to a 3SAT problem is yes, if there is some way to assign true or false to each variable such that the overall formula is satisfied and evaluates to true. And the answer is no if, for any assignment to the variables, the formula always comes out to false. So to prove that 3SAT is NP-complete, we need to first show that it's in NP, and then show how to reduce CircuitSAT to it. In 3SAT, as with other Boolean satisfiability problems, our input is some type of Boolean formula. So we have a bunch of variables that are connected by Boolean expressions. And so, to prove that there is some way to satisfy the formula, we can provide a certificate that says, here are the values to give the variables so that the whole formula comes out true. So our certificate is assigning true or false to each variable, and then the job of the verifier is to check that we have given a certificate of the right format, and that when we plug in the given truth values to the 3SAT formula, the whole thing comes out to true. Proving that something is in NP also required us to show that the certificate has polynomial size, the verifier runs in polynomial time, and the verifier algorithm is correct. The certificate is a truth value for all of the variables, and since every variable has to appear in the input expression, giving them each a truth value takes no more than linear space with respect to the input. So we have polynomial size, and the verifier can check that the format is valid by looping through the certificate and the original problem. And then it can also plug in the true or false to each of the literals in the expression. And since our 3CNF formula is ORing sets of 3 variables together and then ANDing all of them, it just has to verify that each of the clauses has one of its literals coming out as true. And so that can be done in a single scan of the input formula, which is definitely polynomial time. And proving the correctness of the verifier means showing that it says yes, if and only if we were given a satisfiable formula and a proof that that formula is satisfiable. So if the verifier says yes, that means we were given a truth value for every variable, and those truth values caused the expression to come out true. And in the other direction, if we have a yes instance and a valid certificate, then the certificate will tell us how to assign variables to make the formula satisfied, and so the verifier will say, yes, that is a valid proof. So having shown that 3SAT is in the class NP, we now want to show that it is NP hard, which means reducing CircuitSAT to 3SAT. So, to perform this polynomial time reduction, we need to show how to translate any input for the CircuitSAT problem into an input for the 3SAT problem so that the answer is preserved, and do this in polynomial time. Let's remind ourselves what an input for the CircuitSAT problem looks like. In a CircuitSAT problem, we are given a directed acyclic graph of gates, where some of the gates are inputs, and one of the gates is an output. And for every gate other than the inputs, we have a Boolean expression and or not. Gates can have any out degree, but the in degree is 1 for a NOT gate and 2 for AND and OR gates. And the goal of the problem is to determine, is there some input that will cause the output gate to be true? So our polynomial time reduction will be an algorithm that takes a circuit like this as input and spits out a 3CNF Boolean expression where the expression has a satisfying assignment if and only if the circuit had a way to output true. Our first step in this translation is to figure out what are the variables of the Boolean expression, and we will have a variable for every gate in the circuit. So if we were translating this particular instance, we would create 9 variables. But remember that what we're really writing is an algorithm that will take as input any circuit and will spit out the corresponding formula. And so now we need to come up with Boolean expressions that will somehow encode the meaning of the AND, OR, and NOT gates in our circuit. I realized while editing that I need to interject here because that was not very clear. When I talk about encoding the gates here, what I mean is we want to add some clauses to our Boolean expression where those clauses will be satisfiable if and only if the truth value of the variable is consistent with the functioning of the gate. So for example, on the NOT gate we're about to start with, we want to set up the clauses so that the only way to satisfy them is if the value assigned to the NOT gate variable is the negation of the value assigned to the variable that is being input to the NOT gate. Beginning with a NOT gate, like this one that corresponds to the variable x4, we want to ensure that the relationship between x4 and x1 in the expression corresponds to the relationship between this gate and this gate in the circuit. So we want our expression to enforce that whenever x1 is true, x4 will be false, and whenever x1 is false, x4 will be true. We have to do that using only CNF expressions, and we'll start by not worrying about whether they are 3-variable expressions, and we'll add in the third variable later. So for each NOT gate in the graph, we can build the following Boolean expression. I'm using a bar over a variable to indicate negation, mainly because it saves space. And we've built a conjunction of disjunctions, so this expression is in conjunctive normal form, but it only has 2 variables per clause. And as I said, we'll deal with the third variable later. But for now, let's check that this expression will enforce that xu and xv will be negations. If xu is true, then we want xv to evaluate as false. In this first clause, xu being true means that the clause is already satisfied, so that doesn't impose a constraint on what xv can be. But over here, xu being true means its negation is false, and so if we want to satisfy this clause, we must make this literal come out true, and the only way to do that is if the variable xv is false. And so if it is possible to make xv false, that will satisfy this clause, and if it is not possible to make xv false, then this clause will be unsatisfiable. When we have an OR gate in the circuit, we want to ensure that that variable can evaluate to true if either of these variables evaluates to true, And we can do that with the following clauses. Here we need 3 clauses to ensure that if either of these variables is true, this one can evaluate to true, but that if both of these are false, this one must evaluate to false. If the variables for gates u and v are true and false, then let's think about what happens to these clauses. Well, 2 of the 3 clauses already have one of their literals true, so those won't constrain how xv gets set. But to satisfy this clause, xv has to be true. And so if these are the values of xu and xw, the only way to satisfy the expression is if xv is true. If we swapped which of u and w was true, that would swap which of these 2 expressions was critical, but this one would still force xv to be true. If both xu and xw are true, then these 2 clauses are already satisfied, but the only way to satisfy this one is to make xv false. And conversely, if these were both true, then we would need xv to be true in order to satisfy both of these clauses. For an AND gate, we want to ensure that the only time it evaluates to true is if both of its inputs were true, and we can do that with the following expressions. Here, if one of the inputs evaluates to false, then the to clause with that variable will force xv to be false, and also the third clause will be immediately satisfied by one of the inputs being false. But if both of the inputs are true, then that will satisfy these 2 clauses. But the only way to satisfy the third clause is if xv is set to true. And so we've encoded an AND gate where these expressions are satisfiable if and only if we can match the truth value here to the behavior of the AND gate. We've now described how to deal with each of the gates in the circuit we were given as input, and so to create a single Boolean expression, we AND together the clauses that we created for each of the gates. So for x4, we would create 2 clauses like these that would be ANDed together and would also be ANDed with the 3 clauses representing x5 and so on. The result is a Boolean formula, and we now want to prove that the Boolean formula is satisfiable if and only if the circuit that we started with was satisfiable. If we argue this if and only if, that will prove the correctness of our reduction. And we of course also have to argue that it takes polynomial time. But that's easy because for each gate in the input, we are doing a constant amount of work. And so clearly our total runtime is linear in the input size. The forward direction of this if and only if is that if we can satisfy the circuit, we can also satisfy the formula. And if we have a way of satisfying the circuit, that is a truth value for each input. And so if we give some truth values for the inputs, that implies a truth value for every gate in the circuit, because we can propagate these forward. This one being true means this gate has to be false, and so on. So if we have a way of assigning true and false to the input gates, that implies an assignment of true and false to all of the gates, and therefore to all of the variables in the formula. And if we were to give the values for all of these gates to the corresponding variables, I claim that that would satisfy the formula because we set each clause up so that when we give a value to the previous gate, there is some way to satisfy the clauses for that gate. And specifically, the value that satisfies that expression is the truth value of that gate from the circuit. The reverse implication is saying that if there's some way of satisfying our formula where we have ANDed together all of these clauses, then that corresponds to a satisfying assignment for the circuit. And the way we built these clauses, if we have values for each variable that satisfy the clauses, then those correspond to truth values that are correct in the circuit. But something is missing here. We've argued that if we satisfy all of the clauses, then all of the gates in the circuit are consistent with their inputs, but so far nothing about the formula has forced that the output of the circuit will be true. So we need to add one more clause to the formula that ensures that we can only satisfy it by setting the variable for the output gate to true. If we have a clause with just the variable for the output gate, then the only way to satisfy that clause is by setting that variable to true. And so if we have a way of satisfying the whole expression, then all of the gates will be consistent and the output gate will have the value true, so we can read off from the input variables the inputs that would make the circuit output true. One complication remains, which is that we have several expressions that are not in 3CNF form. Here we only have 2 literals, and here we only have 1. If we were allowed to repeat variables, then we could simply have a clause that puts the same literal again and doesn't change its meaning. But this is typically not allowed in conjunctive normal form. So if we really want to make sure that we have a 3CNF formula, then we need to have 2 variables along with our x out and 1 more variable along with these expressions, where we make sure that those variables will always be false, and that way we can only make this come out to true if x out is true or if one of these literals is true. We can set that up with 4 more clauses where the variables p and q are brand new variables whose purpose is only to enforce that y has to be false. If y is false, then all of these clauses will be satisfied. But if y were true, then no matter how p and q got set, one of these 4 clauses would come out false. If they're both true, this one would be false. If they're both false, this one would be false, and so on. We can do the same for z to get another variable that is always false. And then every time we have either 1 or 2 variables in a clause, we can throw in either y or z, knowing that it will always be false, and get clauses that have 3 variables every time. Finally, I'll conclude by showing the actual expression that this example circuit gets translated into by our formula so that you can check that the same truth assignment that satisfies the circuit also satisfies the formula. So overall, our polynomial time reduction takes as input a circuit like this one and produces as output a 3CNF formula like this one. But we've proven that the answer to this circuit will be the same as the answer to this formula. They are either both satisfiable or neither satisfiable. And that means that we have reduced circuit sat to 3-sat. And that means by transitivity of polynomial time reduction, every other problem in NP can be reduced to 3-sat. So 3-sat is at least as hard as any problem in NP. And now, if we want to prove that further problems are NP-complete, we can use a reduction from 3-sat as a part of that proof.